Hey, how's it going? Today we're going to review the progress of the Hummingbot AI assistant. For now, we're focusing on answering questions about the documentation, and for that we're using Langchain. That is an amazing framework to build applications with LLMs. In this video, I'm going to show you how to load our custom data. In this case, I'm using the documentation that is built on top of mkdocs. So for that, I created a custom mkdocs loader that we're not going to cover into details the implementation, but it's ready to use. You can try it with your own documentation. Then we're going to split the documents in different chunks, get the embeddings, and store them in a vector store. This will let us then ask questions and see which are the documents that might be useful for the LLM to use when we want to answer a question for the user. For that, we're going to try the retrieval QA, the conversational QA, and also build our custom chain to test that out. So let's get started. This is the repository. You can find it under Hummingbot/AI Assistant. And let's cover the main things to get started. First, you will need to create the conda environment. I already have that ready, so I'm not going to do it again. As you can see, it's activated here. But if you need to do it, you have to run conda m create -f environment.yaml. By running this command, it will start. As you can see here, it says conda value error because I already had the environment. But if it's your first time, you should be able to create the environment. Then we will need to add some environment variables. This persist directory is where we are going to store the vector store, and here you also will need to put the OpenAI API key. Now let's start with the first notebook. For that, let me unstash the changes where I have my credentials. Okay, so now I have the credentials ready. So in this case, we have these research notebooks, and explain documentation is a task that we are focusing right now. And let's start with the first notebook. So let's clean all these things. Well, the first part is going to import the main dependencies, load the environment variables. This is not necessary for me because I am running in PyCharm and the path includes the custom loader. But if you're running this in Jupyter Notebook as it is, this is going to add the path so you can import the custom loader. With this, you make sure that the M file is correctly configured. I'm going to comment it right now because I don't want to expose my API keys, but it will show you which are the API keys that you are using. So if we run this command, we are going to start Jupyter. Connection refused, maybe because it's not trusted. Let me try it again. Okay, the problem was that it wasn't trusted. So, now we are going to import this custom loader. I'm not going to enter into much details on here. You can find some examples on Langchain. Here I am using this base loader that will let us load different type of files. And in this case, I created my own class that is mkdocs site loader. For that, I created some methods to do this in a synchronous way or synchronous way. So that is how you can implement the load and load method. But basically what it's doing is based on the site URL, the sections that you would like to filter out and the metadata that you would like to include is going to enter in the website, see which are all the related links, and do a recursive search of all the paths that are available to get the information from all the documentation. So if we run this line, as you can see, we're going to get this website. You can see that this is the website of Hummingbot. Here we have the docs and the academy, botcamp, well, a lot of things here, but we are going to start here in the root and get all the other information. So for that, as you can see, we're going to filter some of the sections because if not, we're going to have a lot of documents. And we're going to run this cell. And then the metadata filter here, I am excluding the related paths and the related URLs because It's a lot of information. Here then, with this loader.load, we're going to load all the documents. So let's run this process. It's going to take a while, so I'm going to fast forward this part. Well, it finished. As you can see, we have some errors. Probably there are some broken links, but don't worry about that. What we can see after this is that we have a list of documents, and we're going to inspect the metadata of the documents. So as you can see, the first is Hummingbot. In the metadata, this custom loader also includes the titles that are present in that page, which is the URL of that page. So as you can see, the first page is hummingbot.org, and the titles are these, the ones that are appearing in that page. The second one is Hummingbot docs, Hummingbot bounties, governance, about, getting started, installation, and well, all the subpaths are also here. So well, I'm very happy with this custom loader. Was my first one. I'm probably going to try to contribute that to Langchain. So we can see that we parsed 238 documents. If we want to spec the first document, we can see that includes the page content and also the information of the metadata. If we want to get only the page content, we can do that. And we're going to see this page content here, probably with print. We can see it a little bit better. So well, now let's see how we can split our document and create different chunks over it. For that, we're going to use this recursive character text splitter. You can see in the Langchain documentation the different text splitters that are available. I read that this is like the most general for text formats, so I like that. And I'm using these separators because I saw that in my text is really present, these separators. So well, I'm going to split the documents. As you can see, the first document is split in 4 sub-documents. So let's inspect what is in each of it. We have here this information, here another part, another part, another part. Well, for now, what you can do here is to change the chunk size and the overlap of the different chunks. Now let's split all the documents with that splitter. Let's use a chunk size of 2000, so we're going to have less sub-documents. Let's run it. We have 5,879 documents. The next step is to get embeddings. If you are not familiar with embeddings, think about it as a numeric representation of the words that you are using. Will let us compare the query that the user is generating with the documents that we have in our vector store. There are different techniques of doing that, and depending on the database that you are using, probably there are more methods supported. We're going to cover that in the second notebook. In order to get embeddings, we need to create this instance of the OpenAI embeddings. I'm also creating this function that will split the documents in sublists of batches of 150. This is because I faced some rate limit issues from OpenAI. Here I put a sleep to wait between each call, but there are some workarounds that I saw in the Langchain documentation, like cached embeddings. So instead of getting the embedding from OpenAI, if I already asked for it before, I can get that information locally. But well, there are some things to explore. For now, as you can see, I have 40 batches and I'm going to run this. This is going to take a while, so also I'm going to stop the video and fast forward that part, and then we are going to see if the vector store is working properly. One last thing before we end is that here we are using this Chroma, that is the vector database that we are using, and has this method from documents. This is going to create an instance of the vector database, and to create that instance we have to specify the collection name. If not, by default I think that is Langchain something. But I think that might be useful if you want to organize all your documentation. For example, Hummingbot documentation, then I can have Hummingbot codebase in another collection. That might be interesting to review. And when you are creating a new instance of Chroma, you can specify which is the collection that you would like to check or have in that instance. So probably it's a good thing to explore too. Then you can add metadata to the collection. And the most important part is which are the documents and the embedding function that you're going to use. This will automatically ask OpenAI for the embeddings and store them in the vector store, so it's pretty handy. And lastly, you can define if you want to persist that vector store, which is a directory. As we know, we have that environment variable that let us define that. So let's run this and see you in a little bit. It finished. As you can see, we have some rate limit issues. So probably I will review which are the methods of throttling that Langchain has, and also the option that I mentioned about persisting the embeddings locally, the ones that we already asked for. But well, now we have this vector DB and we can make our first query to the vector DB to see which are the documents that is retrieving when we are asking, like, how can I configure a pure market making strategy? So if I run this, you can see that we have some documents retrieved. Let's see which is the first one. Page content, pure market making. So well, we have our first system up and running. Now in the next notebook, we are going to analyze a little bit better how we can make these searches over the vector database. Now let's evaluate different retrieval methods. So one cool thing is that here we have already the vector store persisted. Now let's move to the next notebook. We're going to start loading the environment variables. Then this is how we can create the instance of ChromaDB by specifying the collection name, the directory where the collection is, and then the embedding function. We are using OpenAI embeddings too, and this will be useful to compare our query with the documents that we have in the vector store. So here I'm going to run this part. We're going to see how many documents we have. We have 5,879 as we saw in the previous notebook too, so it's all good. This is a query. We're going to check how to configure a pure market making strategy and see which are the documents that appear there. So if we run this, we're going to start with the first method, that is the similarity search. This is going to retrieve the documents that has the higher score of the similarity between the embeddings of our query and the embeddings of the document. So, well, as you can see, it's retrieving the document of perpetual market making, pure market making, pure market making, pure market making. So, well, it's doing a great job, we can say. Let's move on to the next method, that is max marginal relevance search. I only have 4 weeks learning this, so correct me if I'm wrong in what I'm saying. But what I understood is that this fetch k is how many documents we want to retrieve at first based on the similarity. And the final k is how many documents are going to be retrieved. And the idea behind this method is to find the documents that are more different of the initial pool. This is to avoid like redundant information or duplicated documents and try to provide the LLM the most like sparse information possible that is relevant. So if we run this, we can see that we have the config files. This might be interesting, this document, based on the configuration. We will need to see if it's probably good or not. Cross-exchange mining, not relevant. FAQs, what is market making, what I can do with H. Well, probably there are some things that are going to be interesting here. Pure market making, yeah, is going to be really important. And pure market making. So well, the top 2 documents are about pure market making. Then we have FAQs that probably are covering some things about market making. Then cross-exchange mining is not necessary, this one. And this one, the config files, might be useful. The next one is a self-query retriever. Some vector databases accepts metadata filters, and the idea behind this retriever is that, based on your query, can infer with an LLM which is the metadata filter that has to be applied. For that, you will need to define the metadata, each attribute, and the description. Usually here you will need to also include some values that that attribute can take. And then you need to create an instance of the LLM, and with this self-query retriever from LLM, create the instance of the retriever. So with this, check that we are going to get the top 5 documents and print the metadata. So it's getting community calls, I don't know, see later, community calls, and I don't know what else. But as you can see, it's not working as well as the other methods. That I think that is because I will need to specify a little bit better my attributes. I'm not getting here like any information of the values that I can take, but it was just like a try to understand how it works. The technique that we are going to cover is compressors. Basically, this is going to use an LLM to extract the information and like compress that information to then, when feeding the LLM, we are not going to pass all the document entirely, only the things that we might think that are useful. Let's run it and let's check the compressed docs. We're going to get the relevant documents for the query. So, well, here we have some user warnings. Maybe some parties unupdated. Let's see the output from here. You can check. I think that is better structured. We have this. Well, let's see. We have 4 documents only. So, well, after trying this for a little bit and based on the task that I am doing, that is really simple, answering questions about a documentation, I think that I'm going to pick the max marginal relevant search because I don't have to spend API calls to an LLM. It's fast and it's retrieving very good results. So I think that I will start with that and then see if I need an extra complexity. Now let's move to the next notebook to understand how we can use a retrieval to answer the questions for the user. Let's start now with the third notebook. As you can see, I commented this part so you can see my API keys, and we are going to use GPT-4 as a LLM. We are going to create the instance of the vector store 2, as we did in the previous. Now we're going to construct the prompt. So as you can see, it says using the following places, blah, blah, blah. And here we have the context. This is what we are going to get from the vector store and the question from the user. So with this, we can create the prompt. Then we're going to create an instance of the LLM. This that says temperature equal to 0. I learned this from Harrison Chase in the deep learning course. He explains that when we are doing retrieval, we don't want creativity in this type of LLMs or models. So as low as possible, the temperature will be better. Then here we are going to create a chain using the retrieval QA, and we are going to pass the LLM. The vector store, we can use the method as a retriever, and the max marginal search, relevant search, that is the one that we used in the previous notebook. This chain type stuff, also in the course that I mentioned before, is an explanation between the different types of chains that we can use. Well, then extra information. So if we run this, now we are going to ask this LLM if he can explain how the pure market making strategy works. So let's run that. Let's run the chain and see which is the result. Now, if we see the result, says the pure market making strategy involves placing orders on both sides of the trade. You can adjust the order size, price increments, and the number of orders you want to place. The strategy allows for you to inventory skew, order optimization. Is really specific to what Hummingbot offers in the documentation. Now, if we see, we are using 4 documents from the source documents, so also we can inspect them. If we do this, we can see that it is using the description below, showing an approximation of the strategy, inspect the strategy in the code. Well, these are the documents that are retrieved, so you can inspect the results and the source documents. Now we're going to test this conversational QA retrieval. I think that is really similar to the retrieval QA. The only difference is that we are using memory here. So we are going to use this conversational buffer memory, and it's going to store the interactions that we had before with the chain. So to create it is really similar. Conversational retrieval chain from LLM. We pass the LLM, the retriever, and now this memory, that is conversation buffer memory. There are also a bunch of different types of buffers to store conversations in memory. So also all that is explained in the course. We can run this, and now we can ask the question and see which is the answer. One quick error, or this is a small thing that probably might be like noisy for you, is that here we are putting question query, and here is query. But I think that is because of how the chain is created. So it's processing the information. Now let's see the answer. And the answer is the pure market making strategy. Let's use print, probably is better. Print. Okay, the pure market making strategy is a trading strategy that aims to profit from the bid-ask spread by placing orders on both sides of the order book, buy and sell. Here is a general guide on how to use it. Decide how many orders. Well, I think that this explanation is actually better than the one that we have from the retrieval QA, but I would like to really understand why this is better or not, and for that is very good the tool of Langsmith. Let me explain you how you can use it. Let's go to here, Safari, Langsmith, go to app. So here we have projects, and I have this Hummingbot documentation, and we can see each iteration. So for example, here we can get this part and understand what it's doing. So the retriever, the first part, see that if you click here, says question and chat history. That is because we have the memory buffer. So this is the input, and the output is what we saw recently in the notebook. So here, if we check the steps, we have the retriever. So based on this, it's going to retrieve these documents. We can inspect the documents and the metadata. So the first document is add an oscillator. The second document is add an oscillator. And the third document, displaying tokens in balance. The fourth document, the PDF of Hummingbot. So I think that this retrieval wasn't so good as I expected. Then we have this stuff documents chain. That is the documents. We have the LLM chain and the call. So if we check here the call, using the following pieces of context to answer the user question. If you don't know the answer, just say you don't know. Don't try to make up an answer. That is a system message. Here we have the part of the documents that we are sending and the PDF. And this all comes as a system message, all the documents. And here we can see that the human says, can you explain me how to use a pure market making strategy? An explanation of the strategy itself. So, that is how we can inspect what is actually doing our chain. Now let's continue, and now how the order refresh time is going to affect my strategy. If I ask this, let's see what it's going to answer. You can also go here to Langsmith again and see that this is ongoing. This tool is pretty amazing because you can really dig in what the chain is doing, which are the documents that are used, how you can improve the different parts of your chain. So as you can see, it started here. We have chat history. This is really good and means that the memory buffer is working. So this is the information that it's going to use while it's pending. So it ends. Now let's see the answer. The order refresh time is crucial. Determines how often the orders are going to be refreshed in context of liquidity mining or market making. If an order states, is a very good explanation of the author refresh time, and also is using our documents. Now let's move to the last notebook, where we are going to learn the Langchain expression language that I think that is the best way to create your chain, basically because you have full control of all the steps. Start with the last notebook. So we're going to run this. We're going to create the instance of the vector store again. Now we're importing the string output parser. This is to just get the text of the output of the LLM. The template will be the same. We're going to create the prompt that will be from the chat prompt template. We're going to create a chat OpenAI instance with temperature 0. And then the query will be how to use the pure market making strategy. Lastly, the last part is that we are going to construct a chain. As you can see, this syntax that is with this symbol is like chaining different steps, or basically chaining runnables. So with this runnable map, what we are doing here is that the input can be like pre-processed before we pass it to the next step. And this runnable map lets me access to the dictionary. We are going to pass a dictionary as an input, and one of the keys of the dictionary is going to be the question. So as you can see, we're going to use that question to get the relevant documents using the retriever, and that will be assigned to the context key. And then we're going to also pass the question to the next step. So why we need this runnable map? Because we're going to just pass the question. Based on the question, we're going to get the relevant documents and pass the question to, and that will be injected into the prompt. As you can see, the prompt receives a question and a context. So here's the next step. Once the prompt is ready and filled, it's going to pass to the model. We're going to query OpenAI, ask for the result, and then we are going to parse the result as a string. So if we run this, now we can run this part, and let's see the output. To use the pure market making strategy Hummingbot, you need to configure the strategy. Well, as you can see, it's giving us an answer. So it's working. It says thanks for asking, as we mentioned here in the prompt template. So that covers how to load the documents, split them, create embeddings, use a vector store, do retrievals, try the retrieval QA, try the conversational QA, create our custom chain using the Langchain expression language. And now I will show you a very simple web app that we did with Streamlit. That is an implementation of what I showed just right now, but well, it's very simple and just in Streamlit, so you can see how you can put this in production. So here we can run Streamlit run assistant with, I think that this is the command. So now it's working. So here you can select the model that you want. This is pretty simple, nothing fancy. So I will say, how can I configure the pure market making strategy? Let me zoom in a little bit. This. To configure the pure market making strategy in Hummingbot, you need to set various parameters. Here are some of the parameters you might need to set: order levels, order level amount, order level spread. Well, a lot of parameters that I need. For more details, you can refer to the documentation and a link to the documentation. Now let's say that we are going to ask, what is BotCamp? BotCamp is a part of Hummingbot Academy. However, the provided documents do not contain, probably because we filter the things of BotCamp, but here the link sends me to the BotCamp page, so it's really cool. So in order to do this, what I did was to add more details in the prompt and ask that it gives me the link of the document that is using. So the good thing is that I can provide an explanation, but also redirect the users to the specific link. So well, that's all about this experiment that we have been doing with Hummingbot the last few weeks. I hope that we can spend much more time on this. I really like this. So, well, I hope that you like it too, and you can start contributing, adding better prompts, and helping us to create the best assistant ever. Thank you very much.